In this lesson, we're going to continue looking at friction, both kinetic and static, mostly kinetic, and we're going to be combining the idea of friction with word problems that deal with motion equations as well, so acceleration, velocities, that kind of thing. So let's take a look at this first example. 0.17 kilogram hockey puck sliding on an outdoor rink has a velocity of 19 meters per second forward when it suddenly hits a rough patch of ice that is 5.1 meters across. Assume that the coefficient of kinetic friction between the puck and the rough ice is 0.47. We're going to be looking at two different things. We're going to determine the puck's acceleration while in the rough ice in order to calculate the puck's velocity as it leaves the rough ice and returns to the smooth ice. So one thing I'd like to point out here is if you want to write down some notes while we're going through this, I strongly recommend you pause the video. For instance, right now would be a good time, and write down whatever you would like to write down. And you can do that throughout the video as well. If you want to write down some of the solution, you can pause the video and do that. So one of the things that's always good to do is to write out the information that we're given so that we have it accessible and we can choose what formulas we should be using to solve the question. So the first part of the question is asking us to calculate the puck's acceleration. So what is given to us to be able to do that? So if we take a look at the information here, we're given the mass of the puck, we're given the coefficient of kinetic friction, we're given the initial velocity, and we're given the displacement of the puck over the rough patch of ice, which is denoted by these dots here on the line. So if we need to calculate an acceleration, we have multiple ways of doing that. If we had been given enough information of the, like the final velocity, the time, we would be able to calculate the acceleration that way, but we're not given any of that information. However, we are given the mass of the puck and we're given the coefficient of kinetic friction. And if we were to draw a free body diagram of this puck, what would be all of the forces acting on it? So the only force acting on it once it's left the stick is the force of friction, which we know is opposite the direction of motion, which the direction of motion is in this direction here. So we also know that any net force is always equal to the mass times the acceleration. Well, we're given the mass of the puck, it's right here. So if we write that F net is equal to the sum of all the forces, which in this case is just the force of friction, and that's equal to the mass times the acceleration of the puck. Well, if we can calculate the force of friction, we make it equal to mass times acceleration, we can isolate the acceleration in the equation. So that's what we're going to do here. We're going to write force of friction is equal to the mass times the acceleration. Therefore, if we isolate acceleration, we get force of friction divided by mass. Now, you'll notice here that I'm not putting the vector symbols. I'm just doing that to speed things up a little bit. The arrow shows us what direction the force of friction's in. We'll deal with any of the directions later when we actually need them. Right now, we just need to calculate the magnitude of the acceleration, and when we use it in the next part of the question, then we can use the directions. So we know that the force of friction is equal to mu times Fn, and vertically, if we look at the forces on this puck, we have the normal force, which is opposing the force of gravity. The puck is not bouncing up and down as it's going along the ice, it's going straight along the ice, so those two forces are balancing out. So we know that vertically, the net force, which is equal to the sum of the two forces of gravity and the normal force, has to be equal to the mass times the acceleration, but the acceleration vertically is 0. So that means that, oh, sorry about that, let me just fix that. We want to isolate the normal force here. So the normal force is going to be equal to the minus of the force of gravity. Well, the force of gravity is just the mass times the acceleration, which is negative 9.8 meters per second squared, but all of that is negative. So we know that, which I can just basically write as m times ag. okay? So minus m times ag is going to be the normal force in this case. Now, we are not dealing with the direction in this equation. We're just dealing with the magnitudes. So we're just going to put the equation m times ag right in here. And I'm doing that for a reason. Actually, we're going to put it in here because we've already isolated for a right here. We have ff that's equal to mu fn. So mu, but fn is equal to mag, all divided by m. And something interesting happens here. The two masses cancel out. So our acceleration is simply equal to the coefficient of friction times the acceleration of gravity. Now both of those values are given or known. Mu is equal to, and it's the coefficient of kinetic friction here, which is given to us as 0.47, times ag, which is 9.8 meters per second squared. Again, in this equation, we're not worrying about direction. We'll worry about that in a minute. Our acceleration is going to be in meters per second squared when we're done. So I'm just going to multiply 0.47 times 9.8, and that gives us 4.606, which I'm going to keep the full precision that's given to us on the calculator right now. We'll deal with significant digits later when we're actually calculating that value. Now, if you wanted to write a sentence for the first part, you could write the acceleration is, and we're dealing with two significant digits, if I'm not mistaken, for all of these numbers. So you could write it as 4.6 meters per second squared. And the direction is against the motion. Because it is decelerating. Okay? But when I use the new acceleration that we just calculated, I'm actually going to use the 4.606 because I don't want to lose the precision of that number in the second part of the question. So we've just calculated the acceleration. We've done so with the force of friction, which is the only force acting on the puck. If we go back to the second part of the question, it says calculate the puck's velocity as it leaves the rough ice and returns to the smooth ice. So looking at the values that we're now given, we can actually add the acceleration here, 4.606. Now, in this list, we have to remember that the acceleration is against the velocity, so we're going to put a negative sign here to show that. We're looking for the final velocity. Oops, sorry about that. Not zero. We're looking for the final velocity. And if you look at these four variables here, that is now asking you to remember all of your formulas when it comes to velocities, accelerations, and displacements. All right? So that's what we're going to use. We're going to use the equation for, we'll call this part B here. Let's call this part A. Yeah, we're looking for the equation that has VF, VI, A, and D in it. Well, that's VF squared is equal to VI squared plus 2AD. And we are looking for the final velocity, which is already almost isolated. It's the square root of V1 squared. V1 squared is 19 meters per second, or VI squared, I should say, plus 2 times our acceleration of 4.606 times our displacement, which is 5.1 meters. Now we do have to put the direction here to show that it is an opposite acceleration to the direction of motion, which is positive. All right. Once again, this is a really weird equation. We don't usually put the vector signs on top of here, but we do have to use the directions for this equation. It's a special one. If you don't know why yet, we will be talking about it later. But for right now, just trust me, we do have to use the directions. So the positive direction of 5.1, the positive direction of 19, and the negative direction for the acceleration. So if we square root all of those values, so I believe on this calculator I have to put all of the values in. 4.606 negative times 5.1 equals, and then if I square root that, we get 17.7. which we're going to round off to two significant digits, so 18 meters per second, and it is a positive value, so you just put a positive there to show that it's still sliding in the same direction. It hasn't turned around. So this is a good example of a question where we're dealing with both forces and motion, and it shows you how you can find the acceleration using the forces portion of the question and then use that acceleration in the motion part of the question. So those are the types of questions that we can now solve. If we look at this example here, determine the maximum acceleration that can be attained if the coefficient of static friction is 0.70. We're given the mass of the sprinter here. We know that at the point of contact against the ground, even though the sprinter is pushing backwards, the force that's causing, because of Newton's third law, the force that's causing the sprinter to move forwards is equal to the force of friction. So the net force on the runner, if we were to draw a free body diagram, the only force acting on the runner to move them forward is the force of friction. So basically we can say that the applied force is equal to the force of friction, equal and opposite to that. So it's a very similar setup. It's a little bit easier in this case because we're not asking you any kind of motion questions. We're just asking what's the maximum acceleration. So we know that the net force is the force of friction. We know that that's equal to the mass times the acceleration, because the net force is always equal to the mass times the acceleration. Therefore, force of friction is equal to ma, and we can isolate the a again, which is ff over m. We need to find our ff. Well, once again, vertically, we've got the normal force here, we've got the gravitational force here, and as before, I stated that vertically the object is not bouncing up and down. Okay, the sprinter is just moving straight forward at that instant. Therefore, normal force is equal to the gravitational force. So we know that ff is also equal to mu fn. So we're going to replace ff by mu fn. And just like before, because Fn is equal to mg but opposite in direction, it's mag. You divide by m, and once again the m's cancel out. So mu is given to us in the question. It is 0.70. Gravitational acceleration is 9.8 meters per second squared. So once again, this acceleration, we got to be a little bit careful here. I'm not using vector signs when I'm calculating the force of friction, because we have to know that the force of friction in this case is forward, which is the push that's pushing the sprinter forward. So if you want to put a sign, you can do that at the very end, but you really shouldn't carry signs through here. I mean, here's the problem, right? The acceleration of gravity is negative, but that's a downwards acceleration, not a horizontal one. And it's a weirdness of force of friction. If you look in the textbook, force of friction is always usually put in magnitude symbols to talk about just the size of the force of friction, not the direction. We have to use physics knowledge to understand that this 9.8 is no longer pointing downwards. This is going to be our answer for the acceleration in the right direction if you look at this, like eastwards, I mean, if you look at the sprinter's direction here. So pulling out my calculator, I got 0.7 times 9.8. 6.86 to two significant digits, that would be 6.9 meters per second squared. And that is our acceleration. So slightly easier than the previous question because we only had that part. And just to recap, we're taking a net force, saying that the net force is the force of friction because it's the only force pushing this sprinter forward. We know that the force of friction is equal to mu Fn. Therefore, we can replace the force of friction in the formula here by mu Fn, and those are all values that we know. Okay. So here's a question with sleds being pulled. We've done questions like this before. And it says calculate the acceleration of the sleds if the coefficient of kinetic friction is 0.20. Oh, by the way, I should probably go back and mention that this is static friction, right? This is just as the sprinter is about to run, so that friction is always a little bit bigger than kinetic friction. But here we're talking again about kinetic friction. So we want the acceleration of the sleds. The coefficient of kinetic friction is 0.20. So what we can do here is, as we've done, is we're going to find the acceleration of the system, okay, as our first step. And because both of the sleds are tied together, we can do this. And the acceleration of the system is going to be equal to the net force on the system divided by the mass of the system. Okay, well, there are two forces acting on this system. There's the actual applied force of 150 newtons, and there's the force of friction. So we're going to write here net force is equal to the applied force plus the force of friction. The applied force is given to us, but the force of friction is equal to the, oops, that's supposed to be a plus sign there, sorry about that. The force of friction is given to us by mu times Fn, once again. And the Fn is the mass times the acceleration of gravity. But the mass that we're talking about here is the mass of the two sleds, okay? So we're going to have to fix this problem here again. The Fn is not vertical here. This is a term that's all horizontal. So we'll deal with that in the next line here. So our Fn is equal to mass times acceleration, but the mass of the two sleds is 30 kilograms. So the mass of the system is equal to 18 plus 12, which is 30 kilograms. So we're gonna pretend that the two sleds are one on top of the other, and we can do that. We've done a previous question where we were dealing with, I think it was a suitcase sliding across the floor, and we piled another mass on top of it, and basically we just added the two masses together to find the friction on that system. Well, it's basically the same thing here. Friction is acting on both of the sleds, but we can basically just pile them on top of each other and combine the two masses as the system mass to calculate the friction on the system, because friction is only going to be affected by the force of gravity, which in turn becomes Fn. Okay, so 30 is our complete mass here. So we've got mu times mag, but it's mass of the system times ag. And what I'm going to do here is I'm going to draw a quick little free body diagram to show all of that. So this is the mass of the system. We've got our applied force here. We've got our force of friction here. So you can clearly see that the applied force is in the positive direction. If we consider right to be positive, the force of friction is in the negative direction. So we're going to write plus 150 for the 150 newtons here, minus mu, which is 0.20 given to us in the question right there, times the mass of the system, which is 30, times Ag, which is 9.8. I'll just point out once again, we're not using negative 9.8 here because that is the direction downwards, which doesn't work here. It's just a weirdness of force of friction that we don't do that. So if I pull up my calculator again, we've got 150 minus 0.2 times 30 times 9.8, which gives us a total of 91.2 as our net force. And it's a positive value, so that's to the right. And if I now take that number and put it back into my equation up here for the net force, I'm going to get A of the system is equal to 91.2 newtons divided by the mass of the system. That's 91.2 divided by 30. And a newton divided by a kilogram is going to give us a meters per second squared, which I'll write in a second. So let's find out what the acceleration of the system is. So I'll just divide that number by 30. And that gives 3.04 meters per second squared. Okay, so we've got the acceleration of the system, which is part A. I guess I could have just called this part A. And part B is determine the tension force between the sleds. So the tension force is this tension force right here. I'm just going to erase this here. So we've got to draw a free body diagram of sled 1. Now, we've again done these kinds of questions before. However, there is one little thing that's different. Sled 1 is feeling the 150 newtons that's pulling it forward, but there's actually two forces pulling it backwards. We have the tension force, and we have the friction force. Now this is sled 1. Now we could, instead of doing that, we could use sled 2's information, because sled 2 has a little less going on here. Sled 2 has the same tension force, but in the opposite direction, but it only has one force pulling backwards on it, which is the force of friction. So you can actually solve this question in two different ways. You can either use sled 1, and it'll have a slightly more complicated equation, or you can use sled 2, which is what I'm going to do, and just use these two forces here. So you would, if you want to try it afterwards, you can actually get the exact same answer using sled 1. So we know that the acceleration for both of these sleds is 3.04 meters per second squared in the positive direction. Okay. We know that the net force on sled 1 is equal to the tension force, which is to the right, plus the friction force, which is to the left, and that is equal to the mass times the acceleration of the system. Now, in this case, it's not the mass of the system, because we're only talking, oops, sorry, this is supposed to be sled 2. My mistake. We're only talking about sled 2 here, okay? So that's the mass 2 to show that it's sled 2. And sled 2's mass is 18 kilograms, so we'll keep that in mind. We're looking for the tension force, so we're going to isolate for tension here. We've got mass 2 times acceleration minus force of friction. Now, as I've discussed in class, you've got to be very, very careful with minus signs inside of formulas, all right? This minus sign here came from the fact that we took the friction force and moved it over to the other side. So this is an algebraic minus sign. But we also have to include the minus signs for direction. Force of friction is to the left. So mass 2 is 18. Acceleration is 3.04 minus, and in the force of friction, I'm going to put another negative sign to show the direction of the force of friction. Okay, so once again, this minus sign came from the algebra. This minus sign is coming from the direction of the force of friction. And the force of friction is mu times Fn. Now, a minus minus becomes a plus, so we might as well change that right away. Our mu is given to us I've forgotten what it is here. Oh, 0.20. Fn is actually Fg. I'm not going to show all that math again. So Fg is 18 kilograms times 9.8. And again, I'm going to state it once more. The weirdness here of not putting the negative sign beside the 9.8. Because of the way the force of friction works, we do not consider the 9.8 as being downwards and negative. We've taken care of that by setting this one negative here. So if I type that all into my calculator at this point, we got 18 times 3.04 plus 0.2 times 18 times 9.8, and that seems to be giving us 90 as our tension force. Here's another example out of your textbook. 650 Newton student is rollerblading at a velocity of 7.8 meters per second west when the student trips and slides horizontally along the trail, coming to a stop in 0.95 seconds. Calculate the coefficient of kinetic friction between the student and the trail. So we know that coefficient of kinetic friction, mu, comes from the formula for force of friction. Therefore, if we isolate mu, we need to know the force of friction, and we need to divide that by the normal force. But the normal force is the same as the gravitational force, so mass times acceleration of gravity. We can easily figure out the mass of the student, which we'll do right now. So if I draw a free body diagram of all the forces acting on the student, we have the force of gravity, we have the normal force, we have friction, slowing them down once they're sliding in the ground. Okay, so what is the force of gravity on the student? Well, that's given to us. Remember that 650 newtons is the weight of the student, and weight is given as the force of gravity. Okay, so the force of gravity is mag, which is 650. That means we can calculate the mass. Actually, why am I doing that? I just realized, common mistake, folks. We don't need the mass, we just need mag. Well, mag is given to us, which is 650. So I can just plug 650 at the bottom of the fraction here. What we are missing, however, is the force of friction. All right, so we need to calculate the force of friction. Well, horizontally, the only force that's working on this mass is the force of friction. All right, so we know that the net force, we might still need the mass of the student, by the way, now that I think about it a little bit, but let's calculate the force of friction. So F net horizontally, I'm going to write horizontally here, is only equal to FF, and that's equal to the mass times the acceleration. Well, how are we going to find FF if we don't know the acceleration? Okay, we can figure out the mass of the student, but we can't figure out the acceleration without doing some calculations. So this is where the motion part comes into play, right? They gave us an initial velocity, they gave us a time. We also know that they're coming to a stop, so that's our final velocity. So our initial velocity is 7.8 meters per second. I'm going to call that V1. For now, I'll just put vector symbols on there. Our V2 is 0. Our time is 0.95 seconds. And we are looking for the acceleration. So what formula has V1, V2, T, and A in it? Well, if you go back and look at some of the formulas from before, this is the formula that contains all of those variables. V2 is 0, V1 is 7.8, and our final answer you can already see is going to be negative, which makes sense because it's in the opposite direction of the motion in this case. Our time is 0.95. So I take my calculator here and do the calculation. So 7.8 negative divided by 0.95 is equal to negative 8.21. I'll carry one extra decimal place here, but technically speaking, we should just keep this number in the memory of the calculator in case we need it, which I'm going to do here. It's a lot easier on better calculators, but I could just press the M+ here to add it to memory. And I think we can see the memory of the calculator in this case to actually see that that number is in memory. So if we need to recall that number, we'll just press MR. But a lot of the newer calculators make it a little bit easier to deal with this. So that's our acceleration. Now that we have the acceleration, remember we're trying to calculate the coefficient of friction. We needed FF, right? Well, FF is M times A. So we actually run into a little bit of a problem here. If we write the equation that I had set up above for mu, right? We've got mu is equal to FF over Fn, right? Well, the problem is I need to substitute FF in here. And a student might mistakenly say, oh, but FF is equal to mu Fn, right? So if they do that, unfortunately, we end up with a situation here where we have what do they call a recursive problem here, because the FNs are going to cancel out and we just end up with mu equals mu, and that doesn't help me solve the problem. It's like a circular trap that you can get into in mathematics. What we have to do is use the idea up here that FF is equal to ma. We just calculated the acceleration. We are going to need the mass of the student. So let's come back up here and actually calculate the mass of the student, which is 650 divided by AG, which is 9.8. So I'll take out my calculator again. So 650 divided by 9.8 is equal to 66.32. Kilograms approximately. Okay. So we're going to replace FF by the fact that FF is equal to Fnet, which is equal to MA in this question. So if I put MA here, and at the bottom I put MAG. Now actually I don't need the mass. I just realized those will cancel out anyway. Okay. So I'm left with A divided by AG. So what is the acceleration that we calculated? It's the 8.21. And that's going to be divided by our 9.8. And mu doesn't have a direction, so we're dropping all the directions here. There's no vector on top of mu, okay? So I'm just going to go back to my calculator at this point. So didn't actually need the mass. If we go memory recall, which is our 8.21, I'm just going to change that to a positive and then divide by 9.8. That's going to give us our mu of 0.84 if I round that off to, I believe that's what it was. Yeah, if I round that off to 2 significant digits. So you got to be careful sometimes. I did get a little confused myself trying to do this one for a second there, realizing very quickly that if I put mu times Fn right here with Fn on the bottom, I would just end up with mu equals mu, and that doesn't help me solve the problem. So sometimes you have to go find another value for the force of friction, which we have from our net force up here. And you can see that when you put the MA here, the two M's cancel, and you end up with the correct answer that way. So I've given you a few examples of the combination of forces with the motion equations, so you can see how all that gets put together. Hopefully that gives you some starting points for the homework that you're probably going to get with this note. So that'll be it for today for forces. Talk to you soon.